Okie doke. So now you have watched the Amoeba Sisters video that talks about sex-linked traits and some of the differences that we see with creating these Punnett squares and why we actually have specific traits that are only found on those sex chromosomes. So quickly, I want to go through just a few notes so that you have time to work on a couple of practice problems so that you can actually see one being worked out just like we would do in class. So if you look at the sex-linked trait notes and practice that I've sent you, we're going to look at page 1. And at the top of this page, you'll see that there's a paragraph or 2 or 3 kind of giving you, again, some background information. And here on my screen, I've gone through and highlighted just a few of those things that really stand out that you need to know. Basically, genes that are carried on those X and Y chromosomes are considered to be sex-linked. We normally focus, though, on those that are carried on the X chromosome because remember, females are XX, so they have 2 X chromosomes, whereas males are just XY, having only 1 X chromosome. And because of this, we have those instances where a lot of these traits are seen more predominantly in men because they only have the 1 X chromosome. They don't have another allele to be able to either dominate or basically cover up that trait. In females, we do have the 2 X chromosomes, so if a female exhibits a recessive trait, she must be carrying 2 recessive genes. However, if the female is carrying one of those recessive traits, then the other dominant trait will overpower just like we've seen before. However, she will be known as a carrier for this trait and will be able to pass this on to her offspring. Okay? So then down below, you see that there is an example on fruit flies. So I want to touch base on a few of these informational pieces, and then we will work through one that you will be able to refer back to. But you do have all of these steps listed. You're just going to have to make sure and go back and read through this if you're having some confusion. All right, so the biggest thing is what we need to know is females are XX, males are XY. Okay, so that's what we're focusing on. So when we create these Punnett squares, that information must be included because we need to know how many females, how many males are going to be in the offspring produced. And since we are using sex chromosomes as part of the Punnett square in order to not get confused, then we show the alleles for the traits as subscripts on those X chromosomes. Okay, so we're going to have a little bit more information that we've seen before in the monohybrids because we have to still have the information based on the sex. Are they male? Are they female? And then also, do they have the trait or do they not have the trait? Okay, so for this particular question, we're talking about a female who has white eyes. And so we see that her genotype is listed here. And the male is red-eyed because he only has the 1 X chromosome. So he does not have the recessive trait. So his genotype is listed here. Okay? So we put those in the Punnett square just like we've done before. And again, it does not matter if you have male or female on the top or on the side. Okay? That part does not matter. What we see here is that we have the female on top. So we have XX representing that she's female. And then the little r represents that specific allele on that chromosome, in which this case, she has 2 recessive traits. Okay? Same over here for the male. XY indicates that he's male. And then we are only this is an X-linked trait. It's only found on the X chromosome. So that is the only one that has the allele listed as the capital R. Okay? And then you work the Punnett square the same way that we have worked the Punnett squares in the past, doing the cross multiplication. And then step 3 breaks down our ratios. So it tells us that the genotypic ratio is 1-to-1 because our females are exactly the same here and our males are exactly the same here. Okay, so we could list that genotypic ratio as 2-to-2, but if we again reduce to simplified form, then that gives us the ratio here of 1-to-1. All right. Now, the individual female that we show has heterozygous for those traits. Okay, she has a big R and a little r. So she is still considered heterozygous. We're looking at those alleles. Now, that X and Y is just the sex. Okay, we know she's female. Now we're looking at those alleles. So she is going to have red eyes because she has that heterozygous trait. However, this does make her a carrier, meaning if we cross her with another male who has the disease, it's possible that they may pass this trait on, okay? And if we look at the male here individuals, okay, because he only has the one X chromosome, then he is actually going to have the white eyes. So it is the recessive trait. So the male offspring are getting that trait automatically because they only have the one X chromosome, so there's nothing there to overpower it. Okay? So let's take a look at a question, and hopefully this will help make a little bit more sense. So here we have a question on hemophilia. So hemophilia is caused by a recessive allele, all right? And it's given us the letters that we're going to use. Capital N is for normal. Lowercase n is going to be for hemophilia because, again, it told us that it is recessive. So we have a woman who is heterozygous and marries a normal man. Okay? So let's work out what those genotypes and phenotypes are going to be for this particular cross. So first question asks, what are the genotypes of the parents? Okay? Well, a woman who is heterozygous. So first of all, we have a woman. So that means that we have XX. That's a woman. And she's heterozygous. So we need to now put those alleles for that trait as our subscripts. Okay, so she's heterozygous. So that means big N, little n. And our man is normal. So we have man, XY. And he's normal, so that is capital N as stated in the problem. So like so. Okay, so first list the sex chromosomes, then put your alleles for the trait that they're talking about as the subscripts. Okay, so question A is answered there as we added the parents. Now we're going to make the cross. Part B tells us to make the cross. So we're going to have X big N, X big N here. X big N, X little n, X big N, Y, X little n, and Y. Okay? So question C says, what is the chance the child will have hemophilia? Okay? So we need to go back and we need to look at our offspring. Okay, remember, now we're looking at the offspring, so we're looking at what is just in this box here. So in order for that child to have hemophilia, that means that they must have the recessive trait. Okay? So if we look at these individuals here, the only one who has the recessive trait is going to be the one male. So that means that the male who has the X, lowercase n, Y, is the one that's going to have it. So that means that our chances are 25% or 1 out of 4. Okay? The next question says, what is the probability the son will have hemophilia? Okay, well, look at our box again. How many sons do we have? How many boys do we have in this example? Well, this one is a boy, this one is a boy. Okay? How many of those boys are going to have hemophilia? Well, in order to have hemophilia, they must be recessive. So we're going to have 1 out of 2 chance, or 50%, because it asked us specifically about just the sons, not all the kids, just the sons. Okay? Part E, what is the probability of having a hemophiliac daughter? Okay, so again, now we want to look at just the daughters. So we have just the daughters here, the XXs. And in order for them to be, again, hemophiliac, they must have 2 recessive traits. Now we're back to that same rule. In order to be recessive, you've got to have 2 of them. Okay? These girls do not have 2 lowercase n's. So the probability of having a hemophiliac daughter, 0%. So what is the probability of having a normal daughter? Again, we're looking just at the daughters because it's specified daughter. So out of the 2 daughters, what is the probability of having a normal daughter? 100%. Neither one of those girls is going to have hemophilia. And lastly, what is the probability of a son that will not have hemophilia? Again, we're looking at the sons, so the yellow. 1 son's going to have it, 1 will not. So chances of not having it, again, are 50%. Okay, so the big thing here is when you read through these questions, make sure you note the difference between if it asks for a child or it's asking for specifically son or daughter. If it's asking for a child, we'll use the whole entire box. If it's asking for son versus daughter, we only want to focus on those specific genders in that box. Okay? So hopefully this gives you a little bit more clarification. Use this information to help you work through the practice problems that you have in the attached assignment.